Logarithmic functions are inverses of exponential functions. Let's take an exponential function and try to generate the inverse, which will be a logarithmic function. You remember that if we have an exponential function like this and we write it as y equals 2 to the x power, and to generate an inverse we just swap the role of x and y. We let y be replaced with x and x is replaced with y, and now we want to solve this for y. But we have quite a dilemma, don't we, because the y lies in the exponent and we need to enter the exponential world in order to write this as y equals. And that exponential world is the world of logarithms. Now let's leave this problem for a moment and let's talk about the relationship between exponential equations and logarithmic equations. There is an exponential form and logarithmic form that are related. And here's that relationship. We know that 25 is equal to 5 squared. This is an exponential form. The corresponding logarithmic form is this. Now, you may or may not have seen this before, but notice this, that the base of the exponent over here is in this position, and this becomes the logarithmic base, and the exponent is over here to the right. So the logarithm of a number in a certain base is equal to an exponent. A logarithm is an exponent. That's a very important idea in this overall study. Logarithms are exponents. Okay, now we need to be able to go both ways with this situation. That is, we need to be able to go from exponential form to log form and also from log form to exponential form. Let's go through it this way one more time. If x is equal to 2 to the y power, which is what we have over here, then let's see. When we go to the log form, this is the way you might want to proceed, at least at first. You might want to say, well, let's see. This is the logarithm, and I have positions for 3 items. One here, and one over here. And this is the base of some exponent, and that's the exponent. So we look back over here, the base is 2, the exponent is y. So 2 goes here, and y goes here. And the number that we're talking about, it goes in this position. So the log of x in base 2 is equal to y. And we can actually come over here and write that down. We can actually generate, let's do that. Let's slide back over here and replace this y, or excuse me, replace this question mark with, let's see, we had over there y is equal to log base 2 of x. And that's all there is to it. We could call this the inverse function, and we could go through the graph, and we'll look at a graph in a little bit. But let's get back to this transitional idea from log form to exponential form and vice versa. Now, if we're moving in this direction, just recognize that we have base exponent equals that number. You see, so the logarithmic form is saying this is the exponent to which this base is raised in order to give this number. So it's 10 squared is equal to 100. 10 squared equals 100. And for this one, it is, wow, this is rather interesting. We have a base e. Well, certain bases are used so often that they're not even written. As a matter of fact, this is one of them. This base 10 is referred to as a common logarithmic base. It's a common log. And often when it's used, it's not even written. It's kind of like the idea of not writing a 2 when we're talking about square root. You know, when we talk square root, the index of the radical is 2, but we don't write that index. Well, if we just see log 100, it's understood to be in base 10. And if we see log of anything without a base written, then it's understood to be base 10. Now, in a similar way, base e has a very special designation as well. That log in base e of any number here with any exponent is designated as ln. This says the same thing as this. These mean exactly the same thing. This just says that we're talking about a natural logarithmic base involved in this expression. All right, so we would probably not even see log, log, with base e. We would see it as ln x equals b. Now, it's understood that the base is e and the exponent is b, so we have e to the b power is equal to x. Now, let's look at a few situations over here. And again, we're just kind of correlating the idea of exponential form and logarithmic form. We know that in the exponential world that e to the 0 power is equal to 1. How does that relate to a logarithmic form? Well, let's see. We have base e. So when we write logarithm over here, it's going to be natural log. So it's going to be ln. We know this means log base e. All right, good. Now, what's the exponent? The exponent on e is 0. And the number is 1. Oh, so it means then that the natural log of 1 is equal to 0. And actually, that's true with logarithms of all types. After all, any base to the 0 power will be equal to 1, and that base corresponds to the logarithmic base. So this could be 7 to the 0 equals 1, and over here we would have log base 7 of 1 is equal to 0. You see, so it's kind of a commonality that the log of the log of 1, regardless of base, is going to be equal to 0. E to the 1 is equal to e. We know that. So let's write that in log form. Again, it's ln of, let's see, ln means the base is e, the exponent is 1, you see, and the number is e. Oh, okay, ln e equals 1. This is another of those sort of commonalities among all logarithmic bases, that as long as the base here and the number here, if these two numbers are the same, then the result is going to be 1. And it's because of just the nature of the whole idea of logarithm and exponential form. Remember, it's base, this base to that exponent is equal to that number. So if this is 7 and that's 7, 7 to the 1 power is equal to 7. So anytime these numbers are the same, we're going to get 1 as a result. And here's another situation. This is just an obvious condition with exponentials. E to the negative 1 is 1 over e. Translating it over here, well, let's see. Base exponent, base is e, exponent is negative 1, and the number here 1 over e. ln 1 over e, negative 1. Now let's go the other way with a few ideas. ln 4 is approximately equal to 1.386. And by the way, this can be found on your calculator rather easily. There are two logarithmic bases that are contained within calculators. One is the common log base of 10, and the other is the natural log base of e. And if we translate this back to an exponential form, it is now base exponent. So base exponent, that's what you identify first. So it's e to 1.386 is equal to 4. And I probably should say approximately equal to, because this isn't quite exact. Now what about the natural log of a negative number? What would that end up being? Well, let's see. Let's put a variable in here and write it in exponential form and see what this gives us. Let's write this as, let's say n. What number is this? What number goes here? Well, let's see. We would have base exponent, so we would have e to the n power is equal to negative 3. And we're looking for the value of this letter n. Now, we have a positive base, we have an exponent, and we have a negative result. Can we raise 2.7, the value of e, to some exponent and get a negative value? Go like this. No, that's not possible. No matter whether the exponent is positive, negative, or 0, we can never get a negative result. Now that leads us to one of the sort of truisms in the logarithmic world, and that is that we can't take the logarithm of a negative number. The log of a negative number doesn't make any sense. So we say that this is undefined. Now what about ln 0? What does that equal? Well, let's see. We've got, again, we can set it equal to n, and we can evaluate it using an exponential form, which we may understand a little bit better than the situation here. The base is e, the exponent is n, so this is e to the n power is equal to 0. Now, is there an exponent that we can raise e to that will give 0 as the result? And it turns out that it isn't possible. If this is 0, you know, e to the 0 would be 1. And if in any positive number here will give it's going to give a positive value, a value that's not 0. And if we're talking negative exponents, all that does is make a fraction out of this. So again, we're not arriving at 0 with this result. So the logarithm of 0 is an impossibility as well. So we can only take the logarithm of positive numbers. That kind of tells us something about the domain involved in this logarithmic world. How about ln1? What does that equal? Well, let's see. Again, we can evaluate it this way. We might be able to look up here and be able to tell, but I just want to follow through with this kind of line of thinking when we're trying to evaluate a situation like this. Now, we saw this up above, but without going back, let's think about it. This is e to the n is equal to 1. E to the n is equal to 1. What value does this exponent need to take on in order for this to be true? Well, it turns out that e to the 0 power is equal to 1, so ln1 is equal to 0. All right, so some of these things that we saw up here, we can look at another way and get at an answer without actually having to memorize. And I don't suggest that you memorize anything, that you understand it rather than memorize it. Okay, let's look at the graphs. Now, we saw before that graphs of inverse functions have a particular behavior, and they are reflections of one another in the y equals x line. And we're going to find that true with exponential equations and logarithmic equations. Here's the graph of e to the x power. We saw it before. And here is the graph of ln x. Now, these graphs reflect in the y equals x line. And let's take a look at the tables of values involved in these two and kind of verify this idea of reflection and the nature of exponential graphs and logarithmic graphs. Here's y equals e to the x. If we're constructing the graph, the simplest, most straightforward way is to make a table of values. So I would let x take on values -2, -1, 0, 1, and 2. And I've evaluated this expression when x takes on these values to find the subsequent value for y. And we've done this so many times before, this is pretty easy, so I just plotted those points. You see, I plotted the points and then constructed the graph. Now, when we slide over to the graph of y equals ln x, there are a couple of ways that we can proceed. One way is to let x take on particular values, as we did over here, and then solve for y. Just plug it into the calculator. Another way, though, a way that's a little more clever, is to realize that the nature of the relationship between functions and their inverses is that the role of x and y are just swapped. So we could just swap. This x column can become the y column over here, and the y column can become the x column over here. And it's a very straightforward and fast way to deal with this. So we could write this as this. You see, just swap those two. Swap these two. Now, I've already swapped the others, and all we have to do is plot the points, and the points have already been plotted, and the graph has already been drawn. Now, it is probably important to realize relationships between domain and range. Remember that those roles also are swapped when we're talking about functions and their inverses. That is, here for the exponential function, the domain would be all real numbers. That is, we can raise e to any real number, and this makes sense. You see, so it's defined for all real numbers. But the range would be only positive values. You see, only positive values. Now, those roles are swapped when we go over to the inverse function. That is, the domain of the natural log function is the same as the range of the exponential function. The domain, therefore, here would be positive values. And we saw that before. That is, we can only take the natural log of positive numbers. We can't take the natural log of 0, nor can we take the natural log of negative numbers. That's why the graph doesn't appear over here. And then for the range of the inverse function, you see, is the same as the domain up here. So the range is all real numbers. Now, what if we want to construct the graph of another natural log function, or a function involving natural log in the expression like this one? Well, we can use a number of techniques. We can use a point plotting method, and that's probably the safest thing to do. Or we can use the techniques for shifting and stretching graphs that we talked about in an earlier chapter. And you know, all we're doing is comparing this graph with the graph of ln x. You see, we know what ln x looks like. Now, what would ln x minus 2 look like? You see, we have a prevailing operation of logarithm, and we are subtracting 2 before applying that prevailing operation. What does that do to the graph? Well, it shifts it left or right. It shifts in a direction we don't expect. It's going to shift to the right too. So we're taking the graph of ln x and going to the right too with it, and then this outside 2 multiplier is going to stretch the graph. It's going to kind of stretch it vertically. So we can imagine what it's going to look like. We can imagine then that it's going to be this graph, 2 units over to the right, and sort of stretched in this direction. So 2 units over to the right. Now notice the y-axis here is an asymptote. So that asymptote will slide 1, 2 over to the right, and that asymptote then will appear here. And the graph then will snuggle up to that asymptote down here, and it'll go through this point. Oh, but we have this stretching idea, so we're going to end up stretching upward. You see, we're going to stretch this way a little bit. All of these vertical distances defined on ln x are going to stretch 2 units, you see, twice as high as they were before. And we can see it using a table of values. Now, it turns out that if we put in values of x, I have to make sure that x takes on values that will cause us to have a positive number here. So I have to choose values of x that are greater than 2. In fact, I could even write the domain as x is greater than 2. You see, and I could use 2.1, 2.2, 2.3, and so on. But at 2.5, it turns out that y is negative 1.4. And at 3, y is 0. You see, at 3 minus 2, log ln 1, oh, that's 0 times 2 is 0. Okay. And then 4 is ln 1 times 2. Oh, that turns out to be 1.4. Approximately, and 5 goes to 2.2. I just want to jot a few of these down so that I can plot them, and let's come back and plot them. 2.5 goes to negative 1.4. That's roughly right here. That's kind of what we would expect. 3 goes to 0. 4 goes to 1.4, about right here. 5 goes to 2.2. 6 goes to 2.8. So the graph is kind of taking this shape. This is exactly what we expected. That is, the graph is similar to the graph of ln x, but it has moved to the right. It has shifted to the right a couple of units, and now it's stretching itself this way as well. It's probably not surprising that the properties of logarithms are related to some of the characteristics of exponents, because logarithms are indeed exponents. Now, these properties look a little funny if you haven't seen them before, but just hang with me here for a second. There are 3 main properties of logarithms. First one is called the product property, and it is that the logarithm of a product is equal to the logarithm of one factor plus the logarithm of the other factor. Seems totally bizarre until you realize that when we multiply like bases, what do we do to exponents? We add them. So we're multiplying here, and we're in the we're in the logarithmic world, the world of exponents. And so what are we going to do? Well, we're going to add those logarithms. We're going to add those exponents. So that's how we relate it back. Now, there is a proof for this. I don't think it's something we're going to bother with right here, because it's not one that you would tend to remember. You would just buy into the idea that this is a truism in the world of logarithms. Now, sometimes we move in this direction with all of these properties, and sometimes we need to move in this direction. That is, occasionally we need to expand expressions, and on other occasions we need to sort of contract them. You see, and write an expression like this as the logarithm of a single amount. Okay, the quotient property, again related to the idea of exponents, the logarithm of a quotient is equal to the logarithm of the numerator minus the logarithm of the denominator. When you're dividing like bases, what do you do to their exponents? You subtract them. You take the exponent in the numerator and you subtract the exponent in the denominator. It's a good way to remember this property. And once again, this works in both directions. The power property, when you raise powers to powers, what do? Well, you multiply those exponents. And so here we have ln x cubed, effectively raising a power to a power. So this 3 can move into the position of a coefficient. You see, so we're multiplying the exponents here in a sense. So and remember that these can go in either direction for certain purposes. Now let's practice the various properties here. The properties or the expressions which are sort of contracted, we want to expand. The ones which are expanded, we'd like to contract. And this gets us ready for solving equations, and we'll see that in just a minute. Here, the natural log of a radical. Well, gee, we can think of the radical as a fractional exponent. So we have ln x squared plus 1 to the 1/2 power. And now, well, let's see. The 1/2 power can move out here. So this is 1/2 ln x squared plus 1. Now, there is a tendency to distribute the idea of logarithm, but logarithm is not an operation which is distributable, nor is the idea of square root. If we have the square root of x plus 5, we don't say that's equal to the square root of x plus the square root of 5. It's not distributable, nor is the idea of logarithm, and that's one of the most commonly made mistakes in this world. All right, in this one, now this is as far as we can go with the idea of expansion. Here, let's expand this one. We have the logarithm of a quotient. Well, the logarithm of a quotient means that we subtract the logarithms. That is, we take the logarithm of the numerator and we subtract the logarithm of the denominator. Oh, but here we have the logarithm of a product, so we can use our product property to expand this. Now, this is the product of two factors, so it is the logarithm, it is the sum of the logarithms of the two factors. That's what ends up happening here. It's the logarithm of x plus the logarithm of y. And I'm saying logarithm, but you know it's natural log, but it is intuitively obvious that this is the logarithm in base e, which is the natural log. All right, so that's what this is, and bring down the ln5 business. Up here, once again, it's the notion that we have the natural log of a product, and so using the product property, we can kind of stretch it out a little bit. It's the natural log then of x squared plus ln of the other factor. And now this 2 can move into a position of coefficient. So we have 2 ln x plus ln x plus 1. And once again, we can't distribute this ln through that binomial. All right, now let's sort of contract things. Let's bring things together. Let's write this as the natural log of a single item. And to do that, we sort of work the other problems here in reverse. That is, we say something like, well, this 2 as this coefficient can become an exponent on y. So we can write this as ln x plus ln y squared. Now we have the sum of two logarithms, you see, which we can write as the logarithm of a product. So it's ln product of those two, x times y squared. Here's another one. Now we see a difference here involving logarithms, so we might think quotient, 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 and that's going to come in a minute. But we need to take care of these coefficients first. So let's take care of this coefficient. This coefficient becomes an exponent up here. So it's ln x plus 2 exponent 2. And then over here, same idea. ln x cubed. And then this is the natural log of a quotient, and it's x plus 2 squared over x cubed. Now you may be thinking, well, wait a second. Why did I move the 3 up here? Why not move the minus sign with it and make this plus? Could I have done that? Well, it turns out that there are a number of right ways to do these. This is just the most efficient way. You might try that way and see that it comes out the same, but I do want to point out that there are several correct ways to approach these, and if you have a different way, that's great, and it may even be more efficient than the way that I'm working it here. Here are a couple of situations that crop up every now and then. These are just basic truisms involved in this world of natural logs. ln e to the x is equal to x. Now, this isn't something that, it's something that you may bump into from time to time, and you might bump into this, for example, and say, oh, that's equal to x. But if you forget, then here's what you can do. You can say, well, I don't know what this is equal to. Let's just say it's equal to n, and let's find out the value of n. And you find out the value of n by going into the exponential form. So the exponential form, base e, exponent n, is equal to e to the x. Oh, the bases are alike, so if this is to be equal, then those exponents must be alike. So x must be equal to n, or n must be equal to x. So this n must be equal to x. You see, you can verify these ideas if you forget or bump into some difficulty with these things. And in a similar way, we could work this. E to the ln x is equal to x, it turns out, and we can verify that, again, like this. Let's say we don't know what it's equal to, so we would have, let's see, we're going into the logarithmic world this time, so it is ln, base is e, we know that from this. Exponent is ln x. And the number here is n. The natural log of this number is equal to the natural log of that number. It must mean then that these two numbers are the same. So x is equal to n is equal to x. So this n is an x. Okay, so that's the idea. Let's solve some equations. Now, it's interesting that, that solving exponential equations often involves going into the logarithmic form. Solving logarithmic equations often means going into the exponential form. So you just kind of go the other way when you see problems like, oh, this one. You see, it's the idea that the unknown lies in the exponent, and we want to jump into the exponent world. The world of exponents is the world of logarithms. The ticket window into the world of exponents is marked logarithms. And you walk right up to that ticket window and jump in. So here we want to change this into logarithmic form, and it's the natural log form because e is the base here. So it's ln. Now, the base is understood to be e. The exponent is x, and the number is 5. So x is equal to ln 5. Oh, we've solved it. You see, it's done. X equals ln 5, I could write like this. Now this is just a number in the calculator that we can easily calculate, and we could approximate the value of x. We're going to leave it in this form though, because this is an exact value. Now here we would solve this one in much the same way, but before we go into the logarithmic form, we want to isolate the term involving e to some exponent. And to do that, we'll subtract 10 on both sides. So subtracting 10 on the left, we're left with e to the 1/10 t, and subtracting 10 on the right, we're left with 4. I'll go ahead and do the calculation here. And now going into the exponential world, let's see, we have ln, base is e, the exponent is 1/10 t, and the number is 4. So we have this. Now to solve for t, we want to isolate t, and we do that by clearing this coefficient. We clear the coefficient by dividing on both sides by 1/10. Or by multiplying on both sides by 10. You see, this is 1/10, and so we can multiply by that denominator. So this becomes 10 ln 4 for the value of t. Here we have logarithmic equations that we're going to solve, and again, we use the technique of moving into the exponential form. And here we go. ln x equals 9. Well, base is e and the exponent is 9. So we have base exponent equals x. And we're done. You see, this is just, again, a number in the calculator. And we can leave it in this rather exact form, or we can approximate it using the calculator. Now here, as we saw earlier, in order to solve this, we want to we want to go into the exponential form, but don't be too quick to pull the trigger on that. We'd like to isolate or bring together terms and all of that kind of thing. We'd like to have a situation where that we have up here, where we have the logarithm of some amount is equal to a number. When we have that condition, then we jump into the exponential form. So let's see, subtracting 3 on both sides, we would get 2. ln x is equal to 7 minus 3 is 4. Then we would divide on both sides by 2. ln x then is equal to 2. And now here we go. Base is e, exponent is 2, so e squared is equal to x, and we're finished. We've solved the equation. We can use the techniques of this section to find the doubling time of an investment. Let's say that we are investing some money at 6% interest and that it's compounded continuously. Well, under this circumstance and with just this much information, we can figure the doubling time. Now remember, the formula for the relationship between amount in the account, principal, and so on for continuous compounding involves the base e. And it was that the amount is PE to the RT power. And now all we do is fill in. Now, the amount in the account, if we're talking about a doubling situation, then the amount is simply double the value of P. By the way, we could have started with a value, a specific value of P, like $10,000, put 10,000 here and 20,000 here, put 5,000 here, 10,000 here. You see, it's the idea of doubling. But what we can do is very generally say that the amount is going to become 2 times the principal over some period of time equals PE to the RT. Let's see, the interest rate is 6%, and the time is what we're looking for. And now we go through and solve. What we notice is that we have factors of P on both sides, so they will cancel. And now we jump right into the logarithmic world. Let's see, ln base is e, the exponent is this, and the number is 2. So ln 2 is equal to this. To solve for t, we divide on both sides by 0.06. So we have this fraction is equal to t. Now we can punch the calculator and find t to be, I should say, approximately equal to 11.6 years. Doubling time.